In this exercise, we're going to use all of the isomers of C4H9Cl to illustrate some challenges that will be presented with an NMR. Specifically, given a formula and an NMR, we want to decipher the structure. Given a structure, we want to be able to predict NMR. And we also want to be able to make assignments of hydrogens in a molecule, or carbons if we're doing carbon NMR, with the corresponding signals in the NMR that they produce. Now for this exercise, let's start by drawing all the possible isomers that have this particular molecular formula, and let's see if we can figure out which isomer has only one signal in the proton NMR. Take a few minutes and see what you can do. Now the first thing that we might do is to use our index of hydrogen deficiency to figure out whether we have pi bonds or rings. For the purposes of our IHD, we'll turn that chlorine into a hydrogen to get C4H10, and we notice that 10 is double 4 plus 2, so we have no rings, no pi bonds present in this compound, so our IHD is equal to 0. We think about all the possible isomers. We could connect all 4 carbons in a row and then put the chlorine, let's say, at one end. If we put all 4 carbons in a row and we put the chlorine at the other end, we're still actually going to have the same compound. And we'll notice too that we can put the chlorine in the middle, but either carbon in the middle would end up being the same. So let's write in the hydrogens on those two structures. And we could also visualize a structure where we put 3 carbons in a row with a 4th one attached to the center carbon. And if we do that, we can also attach the chlorine to the center carbon, or we could attach the chlorine to one of the peripheral carbons, although it doesn't matter which one, because any one of the 3 that we attach the chlorine to will then give us the same molecule. So those are our 4 possible isomers of C4H9Cl. And the next question, which isomer has only one signal in the NMR, is going to be the one with the highest degree of symmetry. And that is 2-chloro-2-methyl-propane, which has 3 methyl groups that are all carbons with 3 hydrogens attached to a center carbon that has 2 other methyls and a chlorine. So that compound will have only one proton NMR signal. And so it's not going to make a very interesting picture, so we're going to leave that picture off. We might then also consider for this molecule, the first one on the left here that we drew, what might the NMR look like? So let's see if we can predict the structure, or predict what the spectra of that NMR would look like. So if we start with that structure, and I'm actually going to move the chlorine to the other end of the molecule for reasons that will hopefully become evident here shortly. What we're going to find, if we think first about the chemical equivalence, is that we have 4 different signals. So the hydrogens that are closest to the chlorine the 2 on that CH2 that the chlorine is also attached to are going to produce one signal, and that one will be the most de-shielded because it's closest to the chlorine. The CH2s that are one further down the chain are going to be different, and the CH2s that are one further carbon still down the chain are going to be different. And lastly, the CH3 group at the end is also going to produce a unique signal. If we think about sketching these on an NMR or graph of our 1H NMR spectra, the most de-shielded are going to be the furthest downfield or the furthest to the left, the hydrogens next to the chlorine, and they're going to be somewhere around 3 to 4. And so we're going to see that signal in this range. Now notice that that CH2 group has 2 neighbors, and therefore is going to be a triplet. So we'll see a triplet, and the integration ratio, of course, is going to be to represent 2 hydrogens. The second most de-shielded hydrogens are going to be the purple box hydrogens, and they're going to be significantly further upfield, maybe around 2 or a little below. Those actually have 4 neighbors, so we're going to have a multiplet. Technically it has 5 peaks in it, but we'll count 1, 2, 3, 4 many, and that should integrate to 2 hydrogens as well, and that represents those purple box hydrogens. The green or blue triangle hydrogens are further downfield still. They have 5 neighbors, so we're going to have a multiplet with 1 more signal even than the last one that will also integrate to 2 hydrogens and represent that CH2. Lastly, we have the methyl group, which has 2 neighbors and will therefore be a triplet, and that's going to be the furthest upfield, integrate to 3 hydrogens, and those, as well as this other 2 CH2s that we just did, may starting to be running together, so it may actually be hard to distinguish them. So here's an example of given a structure to predict the NMR. What we're going to do next is to, given the NMR structure, we're going to try to match, given the proton NMRs, we're going to try to match these 3 remaining structures to the proton NMRs and to assign signals in each NMR spectrum to the hydrogens in the compound. So see if you can figure out which isomer C4H9Cl is represented by or corresponds to this NMR spectrum. Once you've figured that out, then label peaks that which signals in the graph correspond to which hydrogens in your molecule. With an exercise like this, it's often going to be useful to think about drawing the hydrogens on carbons and to think about what type of a situation that they're in. So we know that we have C4H9Cl. We could go back to those structures and try to match them. The other thing that we could do is to simply use the information that we're presented with on the graph to try to construct the structure. So let's start with the doublet here of 2 hydrogens. What we're going to assume in a relatively small structure is the easiest way to explain 2 hydrogens being equivalent is for them to be on the same carbon. That leaves that carbon attached to 2 other things because carbon makes 4 bonds. Now notice from the chemical shift, this is the most downfield signal, and so this is likely the carbon that bears the chlorine. The least shielded or de-shielded or most shielded signal is this doublet of 6 hydrogens. And the only way to get, or the easiest way rather, to get 6 hydrogens to be equivalent is to have a pair of methyl groups. So we're putting puzzle pieces together, and we know that these methyls collectively have one neighbor. And we know that from the fact that it's a doublet. The last signal here is a multiplet that integrates to 1 hydrogen. So we have a carbon that has 1 hydrogen on it as attached to 3 other things and has a lot of neighbors. So thinking about now how we would put these 3 pieces of our puzzle together, we have 1 piece with multiple connections. We have 3 other pieces that have only 1 connection. So like the corner piece in a puzzle, there's only 1 place each of these can go, which is on the end of a molecule. So in thinking about how those puzzle pieces go together, the CH has to be in the center of the molecule because it's the only one that can be attached to multiple other things. That means it's attached to the CH2 that has the Cl, as well as the 2 methyl groups. And if we think about assigning signals, our 2 methyl groups all come together as 1 signal. Our lone hydrogen here will be another signal, specifically the multiplet with 1 hydrogen. And lastly, the 2 most downfield hydrogens together produce our doublet, and we could label those A, B, C if we wanted. Now let's apply that same rationale to this structure here. Note that this structure also has 4 signals in it, and when we think about our original 4 structures, there were only 2 that had 4 signals, so by process of elimination we can tell what this one is. But let's go through the exercise nonetheless if you want to. Pause the video here and see if you can construct the formula, or rather construct the structure based on the information that's provided. And again, we know that we have the formula C4H9Cl, and so it's reasonable to assume that the most d-shielded signal is due to the hydrogens on the same carbon with the chlorine. And in this case, there's only 1 hydrogen, which we can tell from the integration ratio, but that has to be connected to 2 other things. If we take a look at the next signal, we find we've got one with an integration ratio of 2 that's right next door to a signal with an integration ratio of 3. And in fact, they're so close that they're kind of overlapping a bit. And we might guess that that 3 hydrogen signal is a doublet from the fact that we have 2 very tall signals. We do have 1 bump right to the left, but we don't have a corresponding one on the other side. And so that would be our best guess. But if we didn't know that, let's still recognize the fact that with 3 hydrogens, the simplest way to achieve that structurally would be to have a methyl group. And that can only be attached to 1 other carbon. We're assuming or speculating that it has 1 neighbor. But again, that may not be intuitively obvious to us at this stage. The second structure then has at least, or the second signal down here with 2 hydrogens has at least 4, if not more, peaks. So we're thinking a lot of neighbors. And the easiest way to make two hydrogens equivalent in a small molecule is to put them on the same carbon. That means that carbon would have two other things attached, and since we've already used the chlorine, they'd have to be other carbons. And we assume again, or speculate, that we have multiple neighbors. And lastly, we have another three hydrogen signal. So again, another CH3 is the easiest way to explain that. And notice that this one fairly clearly has three peaks, so a triplet, which means that we have two neighbors. Now notice the difference in those two methyl groups are the chemical shift and the splitting. The one that's further downfield is presumably closer to the chlorine than the other. Now, given the fact that our two methyls are each only attached to one thing, they can't both be attached to the same thing, otherwise they wouldn't be producing different signals. Also, they can't be attached to each other, because if they were, then that would be ethane, and there'd be no way to attach any more elements. So we have to assume that these two methyls are attached to different things. So in thinking of how to put these puzzle pieces together, the carbon with the chlorine has to be attached to the CH2, because those are the only two fragments that can be attached to more than one other thing. So if we move that over so we have room to bring in the CH2, which is our two purple block hydrogens, then we can attach our two methyl groups. And again, since the green box methyl or green diamond methyls are the least de-shielded, or the furthest upfield, we would assume they are the furthest from the chlorine, and that the remaining methyl, our blue triangle hydrogens, must be closer to the chlorine. And when we think about this, we notice that the two square hydrogens and the triangle hydrogen are actually equidistant from the chlorine, which is why their signals are so close in chemical shift. So again, we've deduced a structure given an NMR and a formula, and we've made assignments or correlations between signals in the spectra and the atoms in the molecule that produce them. That means we have only one compound left. We have one more structure in our bank. And if we bring up the NMR that we predicted earlier, we'll find that it matches that the actual spectra matches our prediction quite nicely. So we have one signal integrates to two hydrogens and is a triplet that's the furthest downfield. We have a pair of two hydrogen multiplets upfield of those, and then the most upfield signal we have is a three hydrogen triplet. And the splitting of those is tricky to see because of the resolution of the picture of the spectra as well as the resolution of the NMR from which it was taken, but we can see that we've got a good match here to our prediction.